After the LM Foundation's second part earlier, I'll now, for the next close to an hour, I'll talk about relational deep learning, which is basically trying to understand anything that is concerned with structured data, specifically relational structured data. And in other words, like you would have heard about databases, like it's like a very fundamental computer science course. And in terms of like the modern technology that we have, everything is stored in databases. Like you go to a random restaurant, you buy something and there's an invoice generated, there's a record being entered in the databases. You open a social media platform, message your friend, there's some record going into databases. So databases, how do we understand databases, how do we do end-to-end deep learning on databases? So this kind of next 1 hour is focused on that, and this is also a transition to like some very ambitious applications of geometric deep learning, like graph neural networks specifically, which was covered in the first 2 days. So the outline of this will be like, I'll introduce the setup of like what's relational deep learning, what is the motivation of doing this, some key terminologies. I'll give a quick recap of graph ML models. We won't be going this into detail because of the first 2 days that was specifically designed for that. What are the frontier relational deep learning architectures towards foundation models for relational deep learning? And towards the end, I have a hands-on notebook, which I won't be doing it here for the sake of time, but you can just click on that and then like create a copy of that on Collab notebook and see how to develop a relational deep learning model end to end in just like a very concise small notebook. And that will also be a hands-on of like how a graph neural network can be used to do some prediction tasks on databases. So the motivation of relational deep learning, I mean, we have AI revolution, deep learning revolution, they are fueled by data. And I mean, this is the most valuable resource. Everyone's fighting for data. There's like a lot of big tech industries that are, whenever they see some new companies, they are getting some user bases, and if those kind of data is strategic to what they are doing, there's acquisition is something that they target at. Data is predominantly stored in relational databases, which is there are a lot of tables. Tables are connected with primary foreign key links. Examples in commerce, finance, clinical trials. Examples in other cases as well, like user data. And we are interested in doing predictions on relational data. Like if I have a user transactions, like a sales and products, this is a very simple example, and I want to find out some certain questions that I'm interested in, like which products will a user purchase in the next 7 days, whether an active user will churn off the platform in the next few days, like next 90 days, what will be the total sales of each product in the next 30 days. So these are very valid questions which we want an AI to solve. And we have been talking about LLMs. LLMs doesn't naturally solve these questions because we have multiple challenges, and this is what the session is focused on. But we want to solve these questions because we have very large relational data in the world, and many of them are private data set. But yeah, we want to solve these kind of prediction questions, and we want to learn a user churn model. So the question is, were such models non-existent? No, we already have these kind of models. So traditionally what happens in companies even today, like we have human data scientists who understand databases. They try to convert them into features. They may have to do some SQL operations on databases, convert to features. If they have 50 tables in a database, they would apply some domain understanding in selecting which database rows are important, and they would derive features according to that. And they would use this in traditional machine learning workflows, for example, using a smaller neural network, using a logistic regression or decision tree based classifier, and so on. So there are a lot of disadvantages to this data scientist workflow. The first is like it's a very manual process. There's multiple feature engineering that needs to be done to even develop a very simple user churn model. But we saw in this toy example, there are 3 tasks that needs to be done. So I need to spend time on doing feature engineering for 3 different tasks. And if you think more carefully, if you look at this table for like the next, I mean, if you have time like later, I mean, you think about it, there can be maybe 30 tasks that can be designed for just this. For example, who are who are going to be the top users in the next month? Which user is going to be the most least like who is going to do the least purchase on my platform, and so on. So there are a lot of questions that is of interest commercially. And if you use the data scientist workflow of coming up with feature engineering, it's not scalable. Like I cannot spend time on creating hundreds of models for hundreds of different workflows. And so that's one of the disadvantages. Another is like there's a lot of predictive signal which is missed by feature engineering. So if you are convinced like why deep learning works, or maybe where AI has been headed through like automatic like neural network based approach, is they have kept away feature engineering that had like most of the machine learning workflow occupied pre 2012. Like in 2005, if there was someone doing data understanding, they would develop they would do feature engineering, but over time like models learned like feature representations automatically with neural networks. And the third is like complex deployment as well. Like if I have to recompute features again, I need to follow some non-trivial workflows in doing that can create some issues as well. So how do we leverage sorry, I think there was some noise, but yeah, how to leverage the large scale data that we have in databases without going through the longest duration. We want to apply end-to-end machine learning algorithms that can process data in its natural form, similar to how we get in computer vision models, in large language models. No one is going and building like word features or maybe combining workflows to build word features, but rather we have like very large scale transformers that process data in its natural form. Like we just feed text and we get output as text. So yeah, the goal of this program is to kind of generalize deep learning to relation tables. And even as of 2025, 2024, a lot of if you meet people in industries and ask how do they process relation databases, they would tell the same thing. Like they have feature engineering, they use traditional machine learning models to do that. But we want to kind of improve on that and maybe extract more signal from databases through end-to-end deep learning. And yeah, so relational deep learning is precisely that. It works on relational tables. It requires no transformations, no feature engineering. It can cast the predictive task that I was talking about earlier as graph prediction problems. Yeah, so one question is why we talked a lot about LLM. Why not use an LLM? So people have tried, but then if I want to feed a prompt in LLM, it looks like this. Like I need like at the detail of it, these are JSON objects that have different features like attributes and their values. Some of them are numerical, some of them are categorical, some of them are text. So if there's a table and I need to convert them as a text, the prompt is kind of, it's ignoring a lot of things. It's flattening the structure relationships. For example, I may have a product which was bought in a transaction that involves some other products. So there's a explicit relationships that is very rich, and a lot of predictive signals is kind of coming in that rich connectivity structure. So that's completely flattened if LLM is using this prompt, and it does give some results, but yeah, there are issues, and it leads to very long prompts, which is not readable, which is not what the LLM has been trained to do. Like LLMs have not been trained generally to do these kind of things. So this is a very new prompt. We may get some examples. We may get some results through few shot prompting in this case, but yeah, there are challenges here. So how do we generalize deep learning to relational databases? So that's where the graph machine learning comes in. So a relational database is naturally a graph. Like we don't need to think about it. If I have user tables, sales table and product table with these schema, I may have millions of records of users, like millions of rows, which are like, for examples are here. I may have millions or even more sales records. Some of them are here, and then there are a lot of products that can be in the product table. So if you look at the actual data, like there are like these users who these transactions, like this lady bought a shoe with $8. This guy bought a shoe as well as a glass with some sale records. So it's like a graph. The connectivity pattern here is through primary foreign key links. Like a user, if doing a sale, has a user ID recorded in the sale table, as well as a product ID recorded in the sales table. So the user ID is linked to the sales table through primary foreign key links, and same with the products as well. So this is the source of the graph structure that coming here. So we can just do machine learning on a graph, and we can do all the prediction tasks that I was mentioning earlier in the language of graphs, like user churn, lifetime value of a product, next best action, some link level task, for example, recommendation from some graph level tasks, such as whether a particular sub network is a graph or is fraudulent or not. So we can kind of cast hundreds or even more of these prediction tasks as graph tasks, and we can apply graph machine learning. So that's kind of the key gist. If you have followed like what happened in the day 1 and day 2, you would think that today is the day where you see some real problems, and I'm sure like there were a lot of other problems, other applications that was covered in the first 2 days as well. But this is a area where like every country in the world, every industry in the world has some databases, right? So there's a big opportunity in kind of solving predictive problems here, similar to how LLMs have solved text understanding. And this is what do we use here? We use graph machine learning. I'll kind of show some of the things that have been going on in this domain, like how do we create the graph, how to apply graph neural networks, like how to develop foundation models. So that's kind of the goal of this session. So there are two kinds of graphs in databases. One is the schema graph and one is the relational entity graph. This is a example of a database. It has a transaction table that records transactions, and we can see entities have features. Features can be multimodal, like some of the features may have numerical, some of them have categorical, timestamps, text. There are other tables, like this was transaction table. We can see user and product table, and now the linking happens with like there's a particular transaction record which has one user referenced and one product reference, because whenever a user buys a product, that's what is called a transaction, right? So we see that this is a heterogeneous graph, because there's a lot of nodes, like nodes are equivalent to rows in a table. So there are a lot of user type rows, there are a lot of product type rows, and there are a lot of transaction type rows or nodes. And the links are based on the primary foreign key links. So these are naturally heterogeneous graphs. And mathematically speaking, a database is a set of tables, like there are n tables, and there are links between tables, which is what is called relations. If you remember some high school maths, like relations and functions, this is what a relation is. Like it's a Cartesian product of like these tables here, and we don't have like all-to-all mappings, because the database, like in this case, user is not connected to product directly. User is connected to product through transaction. So the links is a subset of this Cartesian product here. And yeah, so there's this schema graph which would kind of dictate how the graph structure of data looks like. So compared to an arbitrary graph, we also have this unique characteristics that all the data in database graph would be kind of constrained by this schema. If I have this database and I have a lot of records against it, I would never have a user type connected with the product type directly, because it's not there in the schema. So the schema graph is what governs the heterogeneous relational entity graphs. And the schema can be complex. So this is one real example of a clinical trial database. Some examples can be even big. So imagine how badly people are doing relational deep learning, like, or maybe understanding relational databases. Like literally, like there are people in industry who are spending time in understanding these manually, coming up with feature engineering workflows, and then they are predicting these things. So this is highly suboptimal, and the goal of relational deep learning is to kind of address this in a more automated fashion. So the relational entity graph is what the actual data looks like. Like if I look at this is like the relational entity graph, which has all these entities, like 4 users, maybe 8 or 10 transactions, 3 products, and the connections are created via primary foreign key links. So yeah, this is just a mathematical formalization of the same thing. And so the key thing in the last 5 minutes was a database can be converted to a graph by just looking at how the rows are and what the connection between the rows in one table with rows in another table are. So that's the source of the relational graph. And the graph problem is like how do we come up with like a data that can be used for a graph problem. So we can define certain tasks, like how much will each customer buy in the next 90 days, and the labels for this task is automatically present, like it's already present in the database. Like how much will each customer buy in the next 90 days, I can come up with a SQL query that will extract me in a 90-day target for each customer ID at a particular time, what is the value. So this what will make the training table. And the training table, like if I have, let's say, 100 users in my training table, they are coming from the customer table. So overall, I will have the same relational database with the training table and the rows that I have generated from like some queries that that is what the source of supervision is. So if you look at this, you don't even rely on doing manual supervision. It's like automatically we just kind of need to gather the historical targets from the data. And for example, if the question is like predict whether user is going to churn in the next 30 days, we follow the same steps, and we see that like most of these kind of tasks is temporal. So like customers label may change with time. So to define a task, we need the entity with a particular time. Like for example, what was for example, who was Sushila Karki last year? There was a different label, but this year there's a different label, like she's a prime minister of Nepal. So that's also one of the factors, and it says that most of the predictive task with databases comes with a label, a time label, and that's key to handle in defining a task. And yeah, this is again formalization of the same training table. Like we have roughly 3 key attributes or key columns. We have an entity, we have a time against which that data is recorded, and we have the label. And an entity, like there can be the same entity in the training table multiple times, because there can be multiple labels at multiple times as well. And yeah, this is the example of this is the same example. Now this is what now the relational entity graph will look like. So this was my input data. After I gathered the record, I would have a for this particular user, I have on May on June active, on May the probability was churned, and so on. So for each user there can be multiple according to the time, and these are attached in the same graph. So the graph also has certain nodes which have labels now, and the whole pipeline looks like this. So we have the database with the training table that is coming from the like the entity links from the original databases. We give this as the entity graph, like these are training tables, these are the users, these are transactions, these are the products, and we can apply a graph network, because essentially I want to predict based on, let's say these 2 are my training and these 2 are my test. So based on what the label was during the training process, I can predict what is the label of the user A, or vice versa, or maybe user B. So I will take the computational graph, like B is connected to something. So this is how a GNN works. Like for each node, I do a node representation learning by gathering neighbors from one hop, and then for them also they're one hop, and it can keep on for multiple layers. So we can simply apply a graph neural network here. And there's a relational deep learning benchmark that my group has developed in Stanford, and it has a variety of like predictive tasks that can be like used for like toy examples as well. And yeah, if you're interested, you can check this out as well later. So graph machine learning is what we are now coming to. Like, it is the tool that we'll use to learn from the relational entity graphs. And we this with graph machine learning, we are focused now, like it's a unified challenge. Like, if you follow graph machine learning, most of the networks that have been developed are kind of only looking at the static relational structure, but now we require everything. Like, we want to learn the relational structure, we want to learn the heterogeneity of the input data, we also want to learn temporal signals. So we have everything together, and graph neural networks are the way to learn the embedding vectors of nodes based on the original input graph and based on the target node for which I want to learn the vectors. So I mean, this is a quick recap here. I won't go into the detail of like graph neural networks here. I mean, for an input, like GNN can be applied to come up with like vectors, latent vector representations, and we can have node tasks, graph tasks, and link tasks, and we can define most of the tasks that we have in relational databases into one of these three framework. At its core, like a GNN layer does aggregation and update. Graph convolutional network is one of the classical examples where each node, for each node, I do every average aggregation of neighborhood features. So this is through the sum here, and this is the sum of all the neighbors representation. There's a parameter that is used to learn that is what is being learned as part of that neural network. There's a nonlinear activation function. This is the averaging, where each node's degree is used to kind of average the neighborhood features. So the next step is to kind of sum over all the messages from the neighbors and do the aggregation to get the feature representation. So this is just the instantiation of how the GCN works. And heterogeneous GNN is something that can handle additional like aspects. For example, when you are building node representations for user types, you can consider that differently versus product type differently. So the same GCN can be extended for how to say, like for heterogeneous type as well, with multiple relational and edge types. So if we have like three kinds of relations such as buy, review, or wish list in an example, there can be different weights for these three different edges. And it's just an extension of what the original GNN was, and it's telling the model to differentiate by default for different edge types that we are getting. The aggregation, the messaging, it's kind of again similar principles of like what was covered in the first couple of days applies here as well. Yeah, this is some more extensions on that. This is a instantiation of one such example, which is called relational GCN, where we have the different relational type weights. So in the original GCN, we only have one weight, but here we have like WR, which is for different relation types that we have in databases, and so on. So yeah, I'll skip these details for now, because we are more interested in the actual like application of relational deep learning. There's also like a lot of aspects of temporality that needs to be considered. Like they have timestamps, we have new users that that will emerge, and most of the prediction tasks that we want to do must be kind of contingent on certain times. We want to learn temporal patterns as well alongside the structural patterns. One additional observation is that we are actually doing future forecasting. With any kind of relational deep learning task, we are trying to predict the future from whatever data that we have in our databases. So this is another thing. So we have to understand this, and in terms of benchmark design, model design, we take careful consideration to avoid any temporal leakage. Choosing time granularity is also one aspect. So for some cases, for some tasks, like we need very granular time, like 5 minutes or few minutes. For some cases, we may benefit with like 24-hour graph times. So for example, if something needs to be predicted over a period of 90 days or something, we need higher time, like lower resolution of time. For something which are more critical in terms of like days or minutes, we need lesser, and the graph structure also may look different if I'm trying to extract based on some records that I have. So these are just kind of some aspects that is concerned with like relational deep learning, and it also influences like how performance is like there's a benchmark called temporal graph benchmark, and L is for link prediction, and it's a Wikipedia graph where the goal is to do some link prediction. And if the time granularity is chosen on a daily basis, that leads to a best performance on this task compared to some other time difference. So while developing models, how do we encode time is also one of the things. We have time encoders that does it. So we have to make some decision in whether I want to encode the time in hours, days, or months. So that may depend on tasks. And this is the goal of why I'm showing this like last 2 or 3 slides, is to kind of show this is an important factor to consider as well. The time component is also used in neighbor sampling. So if I have a user and I want to apply a GNN, the user is connected with like 10,000 nodes. I cannot operate with all the 10,000 nodes together. I do need to do some sampling. So while doing some sampling, I must be respectful of the time. So like if I'm sampling for a user at like January 20 or maybe January 2, all the data of that user before January 20 should be used for doing the prediction, because because we know like we only want to predict something in the future. So if we're developing a model and we are not considering that, we may leak actually the label that we want to predict from the model. And there are different ways of like doing sampling. So there's another sampler called time context sampler, which is just like based on a query. It will just take like whatever has happened until t-1, and then it will prepare the neighborhood on which like a graph neural network can be applied. But yeah, that was just some aspects of time. Like if I want to summarize, like the granularity of time encoding is important. Time is used for sampling. There are multiple ways that can be done, like considering the graph structure, not considering the graph structure, and so on. So now in the next maybe 10 minutes or so, I'll talk about like frontier architectures for RDL, like what are the models, how are the models being developed to do relational deep learning. So the first is like we can use the GNN off the shelf as RDL model. By using the same workflow, we can have the relational entity graphs. We can use them like for this user to learn from based on this label. I can use the computational graph that is provided for this user. For the same user, I have another computational graph for a different label. So I can use GNN on the entity graph to do node representation learning. It's better than feature engineering because we will get eventually a vector against this node, which was compared to feature engineering. We were doing like maybe some SQL operations trying to extract what is present here, what is present here. It's like row information, and then hand engineering those features. But now what we are having some automated GNN based features for this user, which we can use for the prediction. So this is one difference and one advantage, and I don't have to think about what was important. Like I don't need to think about how to do this SQL construction. I just can use the same graph structure and the input features to get the GNN like features without doing the feature engineering. Yeah, so the same benefits of GNN apply here. Like they can discard certain information that are not necessary, and that they can detect more fine-grained patterns automatically based on tasks, which is important in the local neighborhoods. So they can learn automatically. We don't need to kind of spend time manually in figuring that, except for the fact that like certain hyperparameter optimization is necessary. Across training examples, GNNs can exchange information. For example, if I have a user that was if there's a user 1 that purchased certain products, and the user 2 also user 1 does something else, or maybe user 2 buys certain products, so it can facilitate that exchange as well. We are not just training isolated, we are not just developing isolated features for each of the entities, but rather there's a we are seeing this everything together in in a graph. And that's where, like, if let's say I'm a user, I buy certain products, these products is also bought by in other transaction for different users. So there's those kind of connections are also facilitated across training examples. So there are like very nice workflows by using PyTorch geometric and Railbench. We can come up with databases conversion into graphs. We can use like PyTorch geometry based GNN model. We can evaluate for like node prediction, link prediction, graph prediction. Yeah, so this is like the basic GNN model. And like when this work was done like 2023 or 4, like there was a very significant gain of the GNN model compared to like traditional techniques. So light GBM is like light gradient boosting machines, which involves feature engineering, and it was like which involves feature engineering and the use of like traditional like gradient boosting machines. So compared to that, there was a significant performance gain across the board. So these are like user churn tasks in Amazon e-commerce databases. These are like user repeat, whether like on an event platform a user is going to repeat something or not, whether in an ad platform a user is going to click or visit something or not. So you can see like prior to like using relational deep learning based models, like which is a GNN based models applied on the databases, the performance was around 50s or something for this, but now we get a 20 to 30% improvement in these things, because we're not missing out on signals that was initially like being done by manual feature engineering by data scientists. Same with like regression as well, like some long-term value, these are regression tasks. So we also like observe a lot of performance gain compared to traditional like gradient boosting machines, although regression is a much more complicated task, and none of these values are very good actually. Like there are other issues with regression. I mean, if you would have heard about like how LLMs process numbers. There are specific tokenization mechanisms so that LLMs can give correct numbers, and even if you use today like ChatGPT or Gemini or any other models, they fail utterly on numbers. So I mean, regression has a different challenge altogether. But compared to like traditional models like this, still like we still see performance benefits, and same for recommendation as well. There are performance improvements compared to traditional deep learning models, traditional like database models based on like decision trees or random forests. So the first, yeah, this was like what is the advantage of using GNN as an RDL model. There's some other work that we did as well. So REL-LM is something that we did coming to the same trying to understand the same question: how do we use LLMs to understand relational structure data? So we did some sort of graph rag approach to do this. So the first thing is like they can be converted to prompts, but if you remember the same example of like the whole prompt is very ugly and maybe not reflected of not reflective of what was used for the LM training or fine tuning. So if that text prompt is used, there are issues of flattening, because of which structure information is lost. There's a lot of redundancy. So in this case, if you see, there's like customer ID repeated, and if I'm sampling, let's say 100 customer IDs in a prompt, there'll be a lot of tokens which is repeatedly getting this customer ID again and again and again. So there's a customer ID 13 here, there's a customer ID 13 here, and some information. So there's redundancy. There's a lot of there's long context challenge as well, because for one row, if I consider all the attributes, it leads to a very long information that can otherwise be represented as a simple node and a node vector when we are using graphs. So there are these issues. So how do we use LMs for RDL? We use a graph encoder that converts relational data into embeddings, and we augment these two with an LM. So a graph encoder is used because now we know RDL, we can apply graph ML on databases and we get embeddings. We use GNNs to generate those embeddings, and the output embeddings are fed into an LM. And this is the workflow. Like if let's say my question is something like, will the customer review any product in the next 3 months? How much will this customer buy in total? So I have this input databases. I will retrieve a subgraph against a certain customer, and I will use the GNN. I will get embeddings. Let's say these are all my embeddings. I will project them into a common space of the token embeddings that is given in LLM, and I will feed these as embeddings. So this is called a soft prompt augmentation. Like, we don't have text here. Like in the RAG, or maybe with a few short examples, what we saw that we were giving prompts in the form of text, but here we are giving prompts in the form of embeddings. So this is called soft prompts. Like, we have a question, we have this question, and against that question we are doing a retrieval. We are using a graph encoder to get embeddings, and these embeddings are what is used as prompts alongside the actual text tokens, and then it can give a prediction towards the end. I can have a MLP prediction that will give me whether, if it's a classification task, it will give me like either 0 or 1. If it's a regression task, it will give me the value actually for that. And during this process we can use any open source LLM and attach these embeddings together. There are certain aspects of these pipeline which are trained, such as the projection, the graph encoder, the final head, and certain aspects which are frozen, for example the LLM. So this is a way to use an LLM for answering these questions which we started with in this session. And yeah, it can answer queries in natural language. So this is a way to adapt LLMs for any kind of prediction on relational databases. There are like some certain training stages involved, the pre-training of these the modules that we are actually training, and we are using the same task labels to do the fine-tuning of these projection, the graph encoder, as well as the MLPs. So there's some details. The performance is better than the in-context learning based like the prompt. So the green here is where we use those ugly prompts, like we put everything and pack it as a text. The orange is where we are using these soft embeddings based on GNN, and we can see there's a clear gap. And another thing to notice is that the in-context learning, which is where we are using the text prompt approach, is significantly unstable because we have to make certain decisions. When prompts grow long, we have to decide on how to truncate, what are the important information to keep, what are the other information to neglect, and it has to be done manually. So it involves challenges of like robust prompt design, because of which we see a lot of instability in the green bars versus the orange bars. The orange bars is where the GNN is actually packing all the signals from the databases and feeding it as soft prompts, like in the form of embeddings to the LLM, and we have like lesser instability there. And we will have some more things on like this is sort of a graph RAG approach, because there's a retrieval here which is being augmented to an LLM for generation. So this is also a RAG pipeline, and this is called graph RAG because we are looking at the graph structure of the data and packing into the LLM as a prompt. So we have some more specialized sessions on this on I think Sunday or Monday, when you will hear more from Xavier Bresson, who is also one of the speakers in the AI school. So yeah, moving ahead. So now this graph encoder has to be trained for different tasks. So if, let's say, I have user churn, the graph encoder is only designed for that user churn model. If I have some other like customer long-term value prediction, so the graph encoders depend on individual database and task, which is a challenge, because for certain databases I may need like 100 different I may have 100 different use cases. So it's again not scalable to have 100 different models. So that's where we come towards foundation models. And for foundation models, we develop relational graph transformer, and for relational deep learning, we have like models that can answer all of these predictive questions today, like without doing any external training. So we develop graph transformers specifically for relational entity graphs. And graph transformers, I'll give a very quick background, but you will learn more on a lecture by Xavier later, I think early next week. So graph transformers are better over GNNs in several graph learning problems. We have seen this with transformers compared to RNNs as well. So we develop a relational graph transformer that can understand relationality graph in a much more expressive way. And like attention has like you would have seen this in the first couple of days, that transformers are also sort of graph neural networks. So there's a very close connection. And from graph view of attention mechanism is sort of message passing. Like if I want to develop feature representation of this token, I need to aggregate through all of its neighbors. So a graph message passing also looks like this. So it's very close. And positional encoding are functions of the input data structure. So if transformers word ordering is kind of considered, they can be reconstructed, or maybe how to say, the positional encoding, the sines and cosines that was present in the original transformer is a function of the line graph of the sequence. So if I take a text transformer, I take its line graph adjacency matrix, and I get its eigenvectors. I get a k-dimensional vector for each of the node, which is essentially the sines and cosines, like terms that we get from the original transformer. So this, it looks like this. So this is the six-dimensional vector for each of the token here is encoding the position of a word in the line graph. So we can, if we don't have line graph, if we have a general graph, we can simply obtain these, and that what makes graph transformers. So graph transformer has these attention mechanisms. They have positional and structure encoding that encodes the graph context, and there are local and global representation that is kind of encoded together in the full module. And this is more or less like a kind of quick summary of graph transformer, which again you'll have more in detail. But one challenge is that the goal here is that we want to use graph transformers for learning on relational databases, because we want to use these in foundation models. So like what are the challenges and why do we need a different graph transformers? So in text transformers, an input is represented with two elements. One is token, like the feature of the token. Another is the position, which is represents the graph structure of the input tokens. In the case of like text, it's sequential. So in graph transformer, mostly same thing happens. We just have a graph positional encoding that is not just linear or sequential structure, but rather arbitrary graph structure. But most of these graph transformers are designed for homogeneous static graphs. But for relational deep learning, as I mentioned earlier, we have heterogeneity, we have temporality. So this design needs to be improved so that it can consider these additional structures as well. And if we simply apply existing graph positional encodings, we see they are very slow. Because of the size of the relational entity graphs as well. Like if you consider a very simple case of like some coffee shop which has like some records in databases, and the users, like there will be very easily hundreds and thousands of users, and they have connection, like maybe they're doing millions of transactions for a period of time, and a lot of products. So all of the rows in that database is what makes the total node size in a graph. So these are very large graphs, and if we do the positional encoding computation, it requires additional time, so it's slow. So it's not feasible for large graphs, which is what essentially is present in databases. So we have this relational graph transformer that we developed earlier this year that kind of expands on these multiple information elements, so that each node, whenever I have some user node, these are the local neighbors. For example, if I have a user, these are the products, these are the transactions. So I have a local subgraph that represents a particular user's context. I represent each of the node here with multiple elements. I have node features, I have node type. Node type is what reflects heterogeneity. Hop distance is the graph structure. There's a temporal component, and there's a subgraph based positional encoding, which is encoded by a small graph neural networks. So a node representation is kind of a combination of all these factors, and this is what are the tokens that's fed into the transformer. So these tokens are not exactly the LM tokens. These are like continuous tokens, which is input representation of an entity in a databases. After this, we can apply the transformer with attention networks, like attention mechanism. So relational entity graph is converted to input tokens, which are continuous embeddings of each of the nodes, and we apply a transformer network that has both like local attention as well as a global memory, which is to kind of incorporate certain information which may not be present in the local neighborhood. For example, if I have a user that's connected to 10,000 nodes, in this local context, all those 10,000 nodes are not included. It's only a sample information. So the global centroid is what is kind of approximately remembering what is present in the whole bigger graph of millions of nodes. So the transformer network is something like that. It has both local and global attention, and then it gives the final representations that can be fed into the downstream tasks. So compared to GNN, relational graph transformers improve. So the initial result I mentioned, that compared to the data scientist approach of using light GPMs, we see improvement by using GNN. But now we even improve over these as well by using relational graph transformers, and these relational graph transformers can be used to develop foundation models. There are some additional works that improve relational graph transformers, like by using cross attention and by using temporal sampling. Like they do some more sampling based innovations, like in relational graph transformer we do temporal aware neighbor sampling, but in relational graph perceiver they do temporal sampling, and I mean use the information coming from these both kind of neighborhood, and that's a slight improvement of relational graph transform. So I'm just sharing this in a very quick manner, because these are just like the goal of the last 5 to 10 minutes is to show that we have developed like graph transformers that can be used over GNNs, and these graph transformers are used for foundation models. And why? Because the goal of RDL was to do two things. First was to replace feature engineering, which we did, but the second thing is, like, if I have 100 different models, even if I replace feature engineering, I still need to develop 100 different models. So with foundation models, I specifically want a generalist model. Like I want a generalist model that can work across the things, across different tasks, and that's where we are headed at. And the goal is to bring the success of large language models, vision language models, or maybe vision transformers to relational data, which can enable zero-shot forecasting, which can enable few-shot fine-tuning and in-context learning, so that for structured data, for relational databases, if I want to do predict anything, I don't need to train something else. And this was a advantage, or this was some ability that we had already seen with LLMs. Like 10 years ago, if you wanted a text understanding model to perform some particular task on your specific use case, you would have to train, but now you can just prompt an LLM. So that's kind of the goal, and the relational graph transformer is used specifically in a model called Kumo RFM, which is the first foundation model for databases. It can answer all these questions. So what will user so and so buy next? What will user whether a user will churn soon or not? Is patient in a hospital XYZ at risk of some readmission or not? So these kind of questions can be answered with this Kumo RFM model, and these can be used as like retrieval agents in an LLM framework as well. So there are other like companies like Amazon, Google, all of them have kind of come up with these foundation models. But yeah, I mean the whole idea behind sharing all of these research is that there's, apart from LLMs, there is also this field where there's a lot of data, very large data actually. I mean more than text as well. There's a lot of private enterprise who have a lot of data which are not understood. And how do we solve that? So relational databases can be understood through end-to-end deep learning models these days, and now we even have foundation models that can do zero-shot prediction through in-context learning. I'm missing on a lot of details here because of the time, but this is a very new area of research, and predominantly I kind of work in this area recently during my time at Stanford. So thank you for your time, and I think we almost are on lunch. I can take a couple of questions, just quick. If you have very longer question, I mean, I would suggest maybe let's do offline. But if we have quick, maybe one or two clarifications, happy to take a couple. Or if not, we can. Okay, I think there's some hands there.
So my question is, can you start learning low resource language settings such as Nepali, like training on high resource language and generalizing to low resource settings with minimal data? Can it help?
I don't have a concrete answer to that, because I mean I would have to rely on some benchmarks and experiments. But intuitively, what I understand is, like, if let's say there are token, like the tokenization stage already can encode the Devanagari script or maybe some similar tokens, I can definitely get the advantage of in-context learning. There's no reason why it should not behave like for a same, let's say, the review task, like that I had as an example. If I have a review of a movie and the label is positive or negative, and I'm asking a new question, and all of these, instead of English, if it's in Nepali, and the model, like the LM that I'm dealing with, has seen Nepali content in pre-training, yes, we can get advantage of in-context learning there as well.
And also, training on small data, and we have large language. We are training small data on large language models, and we get a problem like overfitting. Like we have so many millions of parameters, and few data it memorized. How can I solve it? Like freezing freezing some layers can help, but is there any other optimal solution to that?
Okay, so if I understand this question correctly, so how do we solve memorization, something like that, right?
Yeah.
So I mean, it's a very broad question. So there are like a lot of like dropout techniques that's used. Like, I mean, to start with, like we want to make the models not memorized by having some randomness. It can be through dropout. It can be through some sampling, doing the decoding as well. That allows some non-deterministic responses to come. But coming to the question of memorization, I think it's a hard question. What happens is, like, people have different ways of diversifying pre-training data. Maybe yeah, something like that. Maybe like these days, like there are also like mixture of expert-based models that kind of allows some input data to route through different sets of parameters and give answers. So more data, more training. If it's overfitting, maybe if you remember the ABC, like the parameters, the data, as well as the compute budget. So if I'm just scaling in only one dimension, there may be a overfitting. So there needs to be consideration of multiple dimensions as well, in order to not let the model overfit. Like if I have a certain data, and on that model, on a particular budget and parameter size, I have a model trained. If I just increase the data and not increase the other two things, there are like examples empirically where we have seen overfitting. But yeah, I mean, I don't have an answer to the question that you asked. Like the generalization out of distribution generalization is a very hard problem, and I mean, people are still like kind of exploring this.
Thanks.
Yeah. Okay. So maybe last question.
My question is related to your previous lecture.
Okay.
So let's say we have a large language model, and from some parameter numbers, then it shows some emergent property. But when I take that model and maybe distill it down or prune it and make a smaller model out of it, will that emergent property still remain on that smaller model, or it disappears?
I think that there are mixed results for this, and again, like the emergent ability. I think the goal of showing this today was to kind of reflect on the benefits of scaling, to kind of show the benefits of like using large scale models. Model distillation is motivated by the use of by converting this the capabilities of large language models in a smaller parameter regime so that it can work on device, it can work on my laptop, like if I want to run it. So ideally speaking, we want the same capabilities to be retained, and the whole distillation framework is kind of designed with that. So quick answer will be yes, but I don't have a specific like pointer yet, and we need to kind of double check.
So I just wanted to like derive on a conclusion where if the scale is not primary factor, like if the small language models also they retain the same capabilities, then maybe scale is not the primary or intrinsic like, requirement for like achieving the emergence, or maybe it is something else instead of scale. Can you conclude this statement or not?
Let me think. So okay. The question, the opinion here is that scale is not the only thing for emergence, right? I mean, yes, yes, yeah. I mean, there are other things that is kind of, there are a lot of things in the detail that leads to it. The just saying it's only because of scale may not suffice. I mean, there are a lot of like data during the tuning stages that also kind of helps. It's a bit hard to dissect it, and maybe primarily because there's not much theoretical understanding of what is emergence, and it's largely most of the insights that has come is experimental, intuitive. Yeah. Yeah, thank you for the question, and thank you so much for listening to me.